Uh, so welcome, 0 viewers again. But maybe someone will join finally, so I'll wait for some minutes. But okay, while we're waiting, I can just introduce you to the topic, tell you what I'm going to talk about. So yesterday I revised superconductivity. I revised whole condensed matter, and today the idea is to revise superconductivity, and a lot of things happen in superconductivity, so this will be just an introductory video which will give an overview of what's going on in this field, and the focus will be on basic topics. It's still hard to draw a strict border between basic topics and advanced topics, but okay, I'll try, and to some extent I understand this border. Still, there are a lot of topics, so let's just jump into the the condensed matter, as I was showing you last time. And yeah, the second goal is, as previously, to promote focus structure tool, this application that I'm using right now. So let's open some theory about superconductivity, and we'll look about it. So just wanted to make a step back that I have a big special note about superconductivity, and I'm not using that note right now because it's too detailed. We need just some formulas. So right now I will open them, and meanwhile you can see how it works. At least right now this application is still not done, still in the process of development. But okay, we still can see some formulas that I'm going to use. Okay, let's misclick. I need to click on PDF. So that's how I can open very fast some formulas that I wanted to show you. Unfortunately, synchronization is still not fully developed, but okay, it slightly becomes better and better. So okay, let's start with just overview. So yeah, the general overview, what is superconductivity in scope of condensed matter? Well, like I can say that that's the topic that one can study after one learns basic formalism and interaction between lattice, which are phonons and electrons. Then people typically say that the origin of superconductivity is electron-phonon interaction, and that gives us the BCS formula. I mean, the whole BCS theory. And like here you can see that in scope of basics, the BCS theory is second most important theory. Of course, it's not like a good rank. One can say that BCS is the most important theory of superconductivity, but let's not discuss it a lot. In general, we have two theories of superconductivity in basics of superconductivity, Ginzburg-Landau theory and BCS theory. And then there are just applications of the BCS theory, for example, to junctions or to like some thermal properties. And actually there are really a lot of things that happens there. So I just wanted to tell you that there are these two theories. And the first theory, Ginzburg-Landau theory, is a well-known theory of phase transitions, which is now more applicable for general case of phase transitions, not just for superconductivity. But but BCS is a purely theory of superconductivity, and it originates from deep understanding of how electrons and phonons can interact. It's a very not easy question how to derive such model from electron-phonon interactions. But okay, at least currently everyone who knows superconductivity will no doubt that non-modified, non-exotic superconductivity is because of electron-phonon interactions. Okay, so let's start maybe with just revision of why is it here? Okay, I misclicked. I wanted to click here actually. That's already opened. Okay, so mm, let's maybe finish with overview, and then we will maybe understand some main formulas of superconductivity. Mm, so from the big perspective, superconductivity is Ginzburg-Landau theory or BCS theory. These are two theories, and then there are some applications, for example, to tunneling junctions, um, or for example, to vortices in type 2 superconductors. So there are questions how much current flows from one junction to another. Yeah, for example, how field penetrates a superconductor. Then, of course, there are a lot of advanced topics, which is better not to even mention right now. Okay, this is just about Fermi liquid. Okay. Um, I'm not sure how to really introduce this topic. Because, okay, in a very nutshell, yeah, so in a very nutshell, BCS theory starts with discussion of Cooper pairs, where we introduce a wave function for Cooper pairs, and then we come to the gap equation. Okay, let's maybe keep these formulas open, and for the reference we can open them here, and we can look at the final formulas. But during my talk I'll better look at the theory, and yeah, that's the part that I planned to revise right now. What's really going on in superconductivity, and here is the structure of superconductivity. So the BCS formalism is also called microscopic formalism, and as I said, the idea of the BCS formalism, okay, of course there are some just experimental properties which we should know from our general awareness, and these properties should be driven from theory, but right now I don't want to discuss a lot of these experimental properties, because the idea of this stream is to give an overview of what's going on in general in the field of superconductivity. And this is useful to not to be lost in the information, and then if next step will be understanding really what are the physical effects, and they're also actually very well known, so ChatGPT or any other lecture will tell you, or even at the end I can answer some questions about it. Okay, so there are several approaches to the microscopic formalism. and they're not really well consistent one with another. At least it will take several months to understand how they're consistent. One of the approaches is the approach of Green's functions, and um, there are a lot of complicated formulas, so we'll look at them later. So it's possible to use that formalism that I was telling in the previous stream about Green's function method. Um, that's the famous derivation from Brikosov, Gorko-Zelashinsky book, and there are a lot of consequences from this formalism. Right now, I just wanted to tell you that this BCS formalism can be viewed from the Green's function method. Also, it can be viewed just from Bogoliubov transformations. And when we just do transformation, diagonalize Hamiltonian, then we are happily moving somewhere next. But it's actually not really clear what we can do if we don't use the Green's function formalism, because yeah, we can find like gap, how it depends on temperature, but I don't know what we can do later. Maybe we can calculate some current, but it's still not clear how exactly to do it. Okay. Um, um, okay, there are some phenomena which can be explained by BCS theory. Um, Maybe the most important phenomena is the Josephson effect, which is the effect of how current depends on phase differences between superconductors. Okay, we can go to it later. And um, okay, the Ginzburg-Landau theory is easier than BCS. It uses an idea that we have just an order parameter, and to have a phase transition, it should be the free energy should be expanded in some particular way of this order parameter, and everything is created around it. And then there are a lot of applications like fluctuation effects or some like applications junctions, quantization of magnetic field, and something else. Yeah. Okay, in scope of basic topics, I also select kinetics of superconductors. So type 2 superconductivity is about basically vortices, because right now if we have vortices, we have penetration of magnetic field, and usually for typical superconductor there is no penetration of magnetic field inside of superconductor. But there are a lot of things that are written about type 2 superconductors where there is a penetration of magnetic field. Well, kinetic of superconductors is a topic where we have some non-equilibrium phenomena, for example, because of electron phonon scattering, or like I mean scattering of electrons on something else. And then a lot of things are known about junctions. What if we have like resistance? What if we have a capacitance there? What if we have loop of junctions, which is known as squid? What if we use the microscopic formalism, which uses some ideas of Andreev reflection? And basically, these are all basic topics. However, it's still, like, of course, it's not clear how to draw a border between basic and non-basic topics. But advanced topics are even more advanced than the ones that you have seen right now. Because basically there are uh, there is just understanding of phenomena that like field penetrates this way of superconductor, or current flows through some junction of superconductor and normal metal according to this or that rule, or like amount of current is decreased or increased as a function of temperature by this or that value. So maybe we can select, like, first of all, amount of basic phenomena, second of all, the microscopic formalism, which has some philosophical idea that electrons and phonons interact. Then it has some um, special frameworks in scope of which we can work with this microscopic formalism. Sorry, the one of approaches is that we can think about it as a part of the Green's function formalism, which is a general formalism for condensed matter. And second approach is when we write the operator value Hamiltonian and then transform operators and basically diagonalize Hamiltonian. It's also really not clear how useful each of them is, because even if we speak about Green's function approach, we still need to have some extension of this approach to make it really useful. But I will tell later about it when I'll be discussing the Green's function formalism. And the second approach, and the third point which I wanted to tell you, is the Ginzburg-Landau approach, where we have continuous model where there are no operators, but just order parameter, and we have expansion of self-energy. And okay, it's possible to deduce some thermodynamic properties using just this effective macroscopic theory. Then there could be some non-equilibrium phenomena, there could be some vortices, there could be some extra effects, and of course junctions, because there are a lot of physics. There is a lot of physics in the junctions. Okay, in advanced properties of superconductors, we have some disordered systems, because, well, that's like a typical question, like what if we have more impurities in the superconductor? Maybe it will have some different properties. And turns out that yes, there are really a lot of different properties for superconductors with disorder. It depends on the type of disorder, and it's well known for a very complicated diagrammatic approach. Maybe we will look at it. Then there could be some questions about magnetism, and and there are really a lot of things that happens there, but I'm not going to cover anything else in this review, because I'm not sure even how much time will I have for even this review. And if you have some questions, you can write them in comments. I will read them and try to answer. But I'm not telling you that I'm an expert in superconductivity. I am just aware about many topics. And again, the idea of this video is to make this complicated field more clear and more structured, and to show like which topics are there, which main ideas are there, and all of these chapters were taken from different books, so you can also see how they are similar or different from one book to another. Okay, so, and of course a lot of things are not really fully written in this note, because that's not the idea to make it finalized. The idea is to make it as a base for research. So if I need some topic, I just take it and think about it and use in my research. If I don't need, then I'm aware about the topics. But I wasn't thinking finally, like finalize my understanding of a lot of topics. So let's jump to the microscopic formalism of superconductivity. And right now we see theory from book by Abrikosov, Ugarkov, Dzelashinsky. And I can even give you a preview. That's the book, if it tells you something. It's a famous book about condensed matter, which is written by students of Landau. That's how they proposed us to see superconductivity. That everything starts with general model that we have electrons and phonons. They interact through this term. And yeah, like you should know some formalism in general to understand what I'm talking about. But if you don't understand, I think it can not be a big problem, because you can just grasp concepts, right? Like if I tell you that some interaction can be encoded in this formula, and this formula can be plugged to another formula, and that's how you can deduce some physical properties. That's already enough to approximately understand what's going on here. And it's approximately hard to understand everything what's going on here, because I mean, even I wasn't thinking yet about how exactly this formula works, but I will tell you what I know about it. And I haven't seen actually that exactly this formalism which is written here is used. A lot of similar formalisms are written here. I used, but with this theta functions, it's not really well used formalism. So idea is that we can rewrite this Hamiltonian in this form, where we have uh, where we for some reason change the phonon field to electron field, and then we also have some indices. Okay, it's really not clear why did they write it like this. Okay. But no one asks me questions, and that's good. It means that everything is clear. Of course, it happens because there are exactly 0 viewers, but who cares really? Like, I'm doing science, and there is some value in what I'm talking about. Okay, so that's not the only way how we can start working with superconductors. The second approach is from famous book by Levitov and Shitov, where we immediately already understand in the beginning that in the whole formalism of Green's functions, there is a vortex part, and vortex is something that um, uh, reflects the interaction. And if we have a singularity in vortex part, it means that we have some bound state, and somehow it is connected with this general philosophical idea that electrons are bound through, like, because of their tiny interaction one with another. And that's already enough to be very motivated to look at bound states. And like the vortex function. Oh yeah, I see that. Thank you, 0 viewers. But I understand that I'm a little bit having my head near the formula, so I should move a little bit. So that motivates us to, okay, maybe I can do like this, or next time I will decrease the camera. Okay, maybe slightly lower. Okay, so we write an equation for vortex part, and then we use perturbation theory for vortex part, and we get the more exact equation. If I do like this, maybe it will be better. Okay, by the way, it's not in English here, but it's a special complicated theory, which maybe, so it's not, I'm not sure, is it worth it to translate to English or not, because I don't know anyone who was using this theory, I mean exactly in this way how it is written. And oh yeah, that's finally better. When yeah, when I moved myself to the left or to the right, based on how you see me. But okay, the idea is that we start with vortex function. It's I actually tried several times to find out where exactly in the formalism of condensed matter we have this recipe to really start from vortex function, but somewhere there something similar is written, and right now we should just believe that that's the proper starting point. Okay, of course it's written in that book Abrikosov, Горького, Dzelshinsky, which I just told you, but maybe it's not really convincing to just say these words, and we can later look more on what's going on in that book to find out the exact place where this thing is written. But the idea is that like if we want to calculate something exact, then we use perturbation theory, and that's how a lot of interactions can be taken into account. And the vortex function that we really need is this one, and not just this one, which corresponds to just first diagram. So if you're lost, I just wanted to remind you conceptually that we have a formalism which is called the Green's function formalism. And in this formalism there is a special vortex part. And if this vortex part has divergences, then we have a bound state. And we really believe strongly that if there is a bound state, then there is a non-decaying current. It's not really obvious why it is so, but and I actually wasn't thinking about how to explain it so, because yeah, like the typical answer is that electrons are gapped. I mean, excitations are gapped from the all electrons, and to excite the electrons, you need more energy than there is there in the system. So that's why the electrons are not excited. That's why they're all in the ground state, and the ground state is one state, so it doesn't have a resistance. And the thing, of course, like we're speaking about BCS picture, and in scope of this picture, exactly this is what happens. But later I will write better explanation, maybe the same explanation, but in better words, why we are really so motivated to look at bound states of electron. Well, maybe because of just this attempt that, yeah, like if we have a bound state, then then energy of this bound state is lower than energy of excited state, then this is also a ground state. And if everything is in the ground state, then Oh, there is one viewer who joined. I don't know who he is, but hello. If you have some questions, then you can ask me. Okay. Uh, okay, no, he didn't join. He went away. Okay, that's fine. So I was telling that um, finally, anyway, we really believe that um, that we need to find the vortex part, and we really believe that there is a perturbation theory for vortex function. That's how we can get some equation for a vortex function, which will later be useful. Okay, right now we see a more famous version of the something that we have seen before. That's like approximately initial Hamiltonian, which tells us that we have electron phonon interactions. But right now, like, yeah, I wasn't thinking a lot about this formula. Uh, yeah, like somehow it's obtained from here, but here we clearly see the phonon field, and here we don't see a phonon field, we see just electron field. But let's just forget this feature, which I can't explain right now. I don't have extra 3 minutes to think about it. So that model uh, can be okay. The yeah, it's just the yeah, it's just the interacting part of Hamiltonian. It can be written in this form where we have a special uh, function of coordinates written here, which is the famous gap. Uh, so it's better to view gap as some physical object which tells us how big excitations are from the ground state. And here it also can depend on the spatial distance. Um, and the main point is that that Hamiltonian that we have just seen can be written as this function. And actually it's an interesting formula for linear response that we can calculate it as just derivative of the this thing. Actually, I can't comment this much. I wasn't using ever this formula, at least in this form. Maybe some transformed formula which I was using was a version of this formula, but no, yeah, I don't really understand this. As I was telling in the last stream, the linear response is very connected to Green's function method, so somewhere there I should write comments about how to get this formula. Right now there is no comments. There are no comments, so I don't really understand. But okay, if we believe that this function um, can be written this way, then okay, again we can use some perturbation approach and draw some diagrams of this type. It's also really not very clear why this formula gives us this picture. And yeah, maybe later I'll think about it more, but in general, the idea is that we just transform this formula and then label one term of this formula. Oh, oh, there is one viewer. Thank you, Marina. I'm glad you joined the stream. But if you have some questions, you can write them. Actually, I can tell you something that is more relevant to you. But also you can write in English. because I think I mean, the majority here don't know Russian. I mean, except, like, of course, there are 0 viewers except you, but later, if someone looks at the stream, they will not see, uh, and they will not understand what you are writing if you write in Russian. Um, but okay, yeah, I was just. Oh, there is something else. Someone else written much. Thank you, Marina. It's very pleasant to hear your comments. Yeah, but like, there is no sense for me to tell something complicated, so actually I can even switch to no, maybe next time I can do a stream about more like easy to understand topic. But the idea of the stream is as I was saying before, um, to give like overview and general understanding of what's going on, and not to really think about what happens in some formulas, why some diagrams are like they are drawn. And it's like not like lecture where I try to teach. It's a free form of discussion where we can enjoy something that happens there, because like it's like general philosophy that I believe in, that people can understand things not very deep, but conceptually, like conceptually, superconductivity, what is it? And okay, yeah, of course it's like scientific stream, but even conceptually you can understand that you can get some value from some formula, because you have a formalism that gives you this value of some parameter, and you can understand that, okay, in scope of superconductivity you have like 5 parameters that sometimes people are interested in, and you don't need to know mathematics. You can just believe that this equation is used to get this triangular parameter, for example, which is called the gap. Um, and then, okay, there are some plots of it. Let's maybe show you. Yeah, okay. Yeah, maybe I can tell you a little bit about what's going on here, because these are relatively easy to understand plots, and they're like very introductory. So, for example, if someone asks you what is a superconductivity, you can answer like this, that no, basically it's obvious. I mean, it's the same thing that we put in the word superconductivity, like conductivity, but very, very good one. So it's when resistivity is exactly 0. So, for example, if like resistivity is like when current flows through a wire, you get some losses to heat, and then current decays after some time uh, because of this resistivity. Like Ohm's law from school, so on, that boring topic. And here we have a different situation where there is no resistivity. Uh, oh, there is someone else. Thank you, Sam. Love Peace SW6 uh, ZJ. Thank you. I'm really glad that today at least there are 2 viewers, and I'm really happy that you are the viewers. But okay, yeah, like, yeah, let's go. It's way better than yesterday, where I was the only one. Okay. Okay, so let the stream be a very introductory, very easy. And by the way, I can also show you some how this application works. It approximately works. That's also like secondary goal of the stream. Uh, but okay, yeah, in scope of introduction, we can start speaking about superconductivity from this plot, where suddenly resistivity is like how much there is like like Ohm's law, like U equal to yeah, how what is the Ohm's law, like current equals to voltage divided by resistance. So this resistance goes to 0, and current goes like mathematically to infinity, but Ohm's law is not applicable for superconductors, so it's just some constant value which doesn't vanish. So that's like the typical plot that if we decrease temperature, resistivity decreases, and then bam, it's exactly zero. Um, uh, yeah, okay, the second plot, maybe this one, top famous plot about superconductors, that like if we decrease the, okay, if we measure heat capacity, and heat capacity is the ability of storing heat if we put heat. Oh, guys, there are so many people. Yeah, it's a phase transition. Yeah. Hello, Mr. Solikidas. Thank you. Yeah. So that's the phase transition here, and here we have a jump of heat capacity. So suddenly there are more heat is being stored in the superconductor if we decrease the temperature, and that's the plot for normal metal. Normally, heat capacity will decrease slowly because of some complicated laws, and for superconductors, that's not the case, and that's one of the typical effect in scope of one of the theories. Okay, so maybe it's better not to talk about these things. So I can repeat what I was telling in the first several minutes, because, by the way, if you have some questions, you can write them. I can switch to your questions. So I was telling in the beginning that there are two theories that are in the basics of superconductivity. It's Ginzburg-Landau theory and BCS theory. So a good thing is that actually there are a lot of papers that are written about superconductors, and we have just two theories that explain explain a lot of things, and we don't need to switch to many other things. Yeah. Okay. Then let's maybe go back to the formalism that I was talking about. Actually, it was approximately the proper section. Just put it somewhere here. So, okay, the BCS theory, if we want to understand it, we have the susceptibility, which can be evaluated in a complicated way through some diagrammatic approach. Susceptibility will later give us maybe some current, and like one term out of this series for susceptibility is written like this. Then some mathematics can be used to show that this term for zero external frequency can be written like this. And okay, that general idea that we should have divergence in vortex part somehow is related to the idea that we should have a divergence of susceptibility, and I'm not sure really how they are connected, because it sounds like a different statement, but it's very similar. By the way, I didn't erase, didn't put a setting that erases messages from the chat. So let's try to switch here, and I will, yeah, I don't know how to erase the messages. Okay, let's go back and try to just continue. Kramer's relation. I know about Kramer's chronic relations. Yeah, which is about susceptibility. I don't know how it is used in this whole theory of superconductivity. It's used for the electric function, and maybe it's used when we discuss radiation of some particle in solid. Yeah, but dear love, P6SW6ZJ, thank you for your comments. It really makes me more the stream more fun than just monologue. Yeah, but I don't know how is it related to superconductivity. I was learning about like it from Abrikosov-Garkov book, Abrikosov's book, Theory of Metals, from Levitov-Shitov book, and I don't know any application of Kramer's chronic relationship in theory of superconductivity. For me, it's just this formalism, which is not really explained here in this book. But it makes sense because if we just believe that we define like this susceptibility, and then maybe just expand this thing, like we have averaged, right thing, averaging, uh, yeah, and averaging includes the Hamiltonian, and it's a little perturbation comparing to kinetic part. So I think I have even done once in my life some expansion, but it's really a good exercise to take this formula with this Hamiltonian and to get this equation. Maybe I will do it once again. I mean, this formalism, I haven't been doing it. I was maybe doing it a year ago in another formalism. Okay, so finally, when we think about divergence of susceptibility, we get the equation which can be used after transformation to get the critical temperature. And that's already an important result, that we say that exactly at this temperature, that effective model is used. Okay, I see a comment. I think this theory is very close for one theorem. The theorem. Oh, dear love, peace, yes, love, peace. So, you know, like I can tell you just based off what I know about superconductivity, and I don't know how it is connected to dissipative fluctuation theorem. It's about like fluctuation dissipation theorem. For me, it's about linear response, and there is a Kubo formula for the linear response. So how linear response is connected to, I mean, dissipation, fluctuation dissipation theorem is connected to Kubo formula. Like for me, it's approximately similar thing. And it's used many parts of science. Like for example, when I was in masters, I was using it for gravitational waves when I tried to reproduce some results of how some mirror fluctuates when we have shining light beam to mirror. So it's really general, and yeah, like I'm not sure. I don't remember any mentioning of fluctuation dissipation theorem and theory of superconductivity. Of course, I can be wrong, but I was like thinking, I don't know, like 100 or 200 hours about superconductivity right now, and a lot of things are way beyond. I mean, they don't mention at all any fluctuation dissipation theorem. But okay, right now we have Hamiltonian. We have strong belief that susceptibility will give us something really useful, and divergence of susceptibility gives us critical temperature. And of course, I'm not spending much time on mathematics and the details because it's really boring. And if you're really motivated, you can find all answers maybe by asking ChatGPT. It's not really the point to be able to reproduce it. The point is that to see a clear picture what's going on and what is connected with what. Okay, as I said, the Green's function formalism is really used for this problem. So uh, there are a lot of ways how we can introduce Green's function formalism, and here I will show you the approach from Levitov-Shitov. And well, there are very famous definitions of Green's functions, and there are two Green's functions. First Green's function is G, and the second one is F. The difference is that G has a psi dagger and F has no psi dagger, just psi psi. There is a formula in your text for linear response. Which formula for linear response? Don't see formula for linear response. This one or which one? Okay, dear love peace. I will return to a comment when you write. But okay, let's just move forward because it's like more abstract question. Is it connected or not? Because in general, we understand how that approach work. The second approach tells us that actually there is a different formula for susceptibility. Susceptibility is a linear response. Yeah, yeah, you can say this in linear regime is a linear response. But it doesn't tell you much because linear response is exact formula that you have a perturbation to the system, then some response is equal to integral of something times this perturbation. And there are some like thermal dependent functions, for example, and that's like linear response. You can ask yourself what happens beyond linear response. It's also a valid question, but I don't know answer on this question. So yeah, like you see, like when you look at this, you don't see anything which is connected to linear response. Maybe you can use some deep understanding of linear response and tell me how these theories are connected, but it's not obvious and it's not really needed. You can just focus on what's going on here and just use this theory. So if we introduce these Green's functions, we have again like averaging. That's how I understand. Yeah, that's the convolution. Yeah, you're right. So I propose to move to Green's function method because it's a very famous method. And also, if you stay longer, I will tell you some versions of this formulas from Abrikosov, Gorkov, Zelashinsky book, and that's a nice exercise. And it's also will be a first ever stream made on YouTube, which compares theory from Levitov-Shitov and Abrikosov, Gorkov, Zelashinsky. You know, like these are secret questions. No one ever tries to point out them because it's hard to understand both of them, and it's not also ever written anywhere written how they are connected. So so that's like 2026, and finally there is a stream on YouTube that tries to compare these theories. So okay, we have this definition of special Green's functions. There are some comments which are written here, and there are comments which are in my head about them. But that's not really essential comments for like understanding. Okay, a second. Okay, so how I understand it, that again, like we have some averaging here, and averaging is made according to our Hamiltonian, which has some perturbation. And if we expand in perturbation, we will get like series where we have averaging in unperturbed Hamiltonian. And that's how we can get the series of Green's functions, of two Green's functions. By the way, one is called normal, another is called anomalous Green's function. And the second thing, which it's also really hard to explain, that the gap is equal to this thing, which this is a anomalous Green's function, and the wavy line is I guess phonon interaction. Yeah, like here you can see that it's just lambda, because this diagram is different from this diagram only by lambda and also squared polarization loop. That's how I can guess that this wavy line is just a lambda. However, it's not written in this text as far as I know. But these are relatively famous diagrams for the gap. You can ask me why this is so. Where does this come from? Uh, uh, yeah, let me not answer this question because I'm not sure where does it come from. It's not a really easy question. There is a self-consistency equation, of course. Yeah, maybe we can even think about it as a definition, because there is a famous understanding of this anomalous Green's function that is really very connected to the gap by just integration of this function. And that's exactly the integration. But it's not a really well consistent written theory here. That's why it's hard to make streams about it. Um, but okay, there is no formula for this expression here, but maybe later we'll see it. And in general idea is that maybe it's a just definition. And reminder is that originally, it's not actually written. Is it written or not? Let me check. Okay, it's not written. That maybe we'll see later that there was, okay, I was telling recently in the beginning of the stream that we have initially this Hamiltonian of electron-phonon interactions, and then we rewrite the phonon function field in terms of electron field, and then we do averaging. That's how I understand it. So that's why this thing is basically should be the gap actually. Okay. Yeah, okay, this is a strange formula because basically we have derivative of a gap with respect to gap. uh, yeah, but gap is somehow something like this actually. Okay, yeah, basically I can use an advantage of my application because here I can easily access some formulas that I was writing previously. And let's just find this formula that will help us understanding. Yeah. Oh, that's the Bogolyubov approach, which we will see later. Um, yeah, so that's the definition of the gap, right? Okay, it's written in terms of such field operators, but here in this notation, yeah, there is another complicated question. Here we have momentum representation, here we have coordinate representation, but still this psi should be the A operator. Okay, let's even not ask this question because I don't know really answer. But yeah, okay, let's just stop on this vague understanding where I really don't know an answer. Um, so let's consider this is just definition. Okay, I can go away of this thing and put some structure here, structure panel. Okay, now we have this equation, which tells us, I guess, exactly what's written on this series. And like here there is the real Green's function, that's anomalous Green's function, and uh, uh, yeah, like it's really also not obvious, so let's just believe authors of like this book. It's from Levitov Shitov, so right, Levitov and Shitov are famous theorists of condensed matter, so they will not lie us, and this equation should pop out of the definitions of Green's functions. Um, okay, oh yeah, by the way, that's the equation that was also illustrated here, that we have the integral of the anomalous Green's function according to some rules, which I wasn't even trying to explain right now. Because of these rules, there is this I. Actually, I also don't really understand why there is I here, but I guess it should be written somewhere in maybe because of Gorkov. I hope so. Okay, then unfortunately I should apologize that I don't have these numbers of equations. That's because of technical error, that I didn't see how the tech was extracted, and it was extracted without formulas, without labels of formulas. So we are left without labels. But okay, just believe me that these are 1033 and 1034 equations. Um, uh, okay, it's really also not obvious why these are the solutions of this equation, but we can see that if we plug f here, then we are left only with equation for big G, and vice versa. If we plug big G here, we are left only with equation for f, and we put always f to the left side, then we divide uh, um, by this. Oh, I have a comment. The main ideas for BCS is to organize BCS Hamiltonian. Well, like you see, actually, dear Mr. Love Peace, I'm really glad that you're so enthusiastic about this topic. Really, I'm glad for your comments. So you see that it's an interesting thing that from one side we are taught that there are Bogoliubov transformations, and this is, by the way, the typical theory that you imagine that look, we have a Hamiltonian, it's not diagonal, let's introduce, here it's B, but doesn't matter, like this field, and now we have mean field approximation, then the first step. And the second step is that we do these Bogoliubov transformations and we diagonalize Hamiltonian. This is our diagonal Hamiltonian. And somehow then if we use this diagonal Hamiltonian for this averaging here for the gap, we get the gap equation, and this like kind of success because we found how gap depends on temperature. But then well, like I was thinking about it, what can we do else? And there is a formula for current where there are some operators, so maybe we can get some current, but okay, I don't know yet how to do it. I was looking several times on these formulas, but I wasn't practicing them. But approximately you can do nothing else in scope of this Bogoliubov theory. Well, like it's really hard to discuss this because I was even reading original BCS paper and they didn't use these transformations. It's actually a fun fact which no one is talking about, that originally this Hamiltonian was analyzed without Bogoliubov transformations and without Green's function method. So I don't know how. By the way, I have in my another note about condensed matter original BCS paper. So if it was another note I would show you, but not to switch too much. I would better not switch. But There are several approaches. One of the approaches is the Green's function that is here. Another approach is just operator approach when you diagonalize it. The problem with operator approach is that you can't plug many properties here. The first example that comes into my head is the example of disorder superconductors, where you have some philosophical ideas that like disorder is like amount of like replicas, right? Like possibilities how material can have one impurity, and this whole formalism is working only with Green's functions. It's not working here. I don't know, and I haven't seen anyone who was doing disorder in scope of just diagonalization. And here you can see a beautiful example that you get the same result as for diagonal for the like Bogoliubov transformations, but absolutely without it. You just need to understand like Green's function formalism on a very advanced level. Wait a second. There are some relations for B and B dagger and for, as I remember, yeah, like that's, I mean, look, this is Bogoliubov transformations, and did I write it here or not? Let's see, no. Yeah, it's like yeah. Okay. Let's go to the formalism of condensed matter. Let's diverge a little bit, but not so much. So actually, what you maybe don't know, but maybe know, I don't know, that there are actually two. Okay. Um, there are two Bogoliubov transformations. Okay, this synchronization is a little bit broken. Sorry. Last time I tried to fix it, but right now no. So there are two Bogoliubov transformations. One are for bosons, another are for fermions. And here I have a nice summary of them. So if you speak about fermions, basically you have the same initial Hamiltonian, right? The kinetic term and the potential term, like dagger, non-dagger. And if you speak about fermionic Bogoliubov transformation, you have minus here, plus here, and relationship is like this with plus. I also, by the way, don't remember it. I just have a formula under my finger for reference. Um, so these are the correct condition for fermionic Bogoliubov transformation. I wrote it, by the way, from Chalker's note of condensed matter. So if you don't believe, you can search in Google Chalker note condensed matter. But by the way, even here in theory of Levitov-Shitov, there should be some. Okay, it's not written here exactly on this page, but somewhere here it should be written. So these are the fermionic Bogoliubov transformations, and the result is that for this template model, yes, of course, for fermions are anti-commutative. Yeah, but I mean, that's of course like this. The question is, yeah, okay, yeah, I mean, it's not, for me, it's not really obvious. I would need to think carefully several times because there's the condition, of course, for anti-commutator, but that this thing with plus follows from this condition. It's not like very obvious. I would need to think like 3 minutes and derive it for 3 minutes to really be assured. And okay, for this template model with epsilon and lambda, that's the result that the Hamiltonian looks like this, where that's the energy, which is square root of epsilon squared plus lambda squared plus some constants. Okay, and the second thing, which is not really relevant at all to superconductivity, is the bosonic Bogoliubov transformations. And the same Hamiltonian, but for bosons will be diagonalized like this. There will be plus plus signs, and uh, the spectrum will be different. It will be no longer with plus, but now with minus. And what I wanted to show you is that, okay, it's shifted from one line to another, but you can see that for bosonic Bogoliubov transformations, you have the minus sign as you wrote. Yeah. So for fermions, we need the plus. Yeah, this one's. Okay, so let's try go back to the to the superconductivity, I mean, scope of Green's functions. So, like we use, so some of our deep belief that Green's function method is really working and useful. Then we write equation for Green's function. We expand averaging with respect to perturbed Hamiltonian into series of averaging with respect to unperturbed Hamiltonian, and that's how we get this infinite series for Green's functions. And then I guess we just see that, oh, actually, look, if we look here, then we have exactly this series for anomalous Green's function. That's how we get these two equations. That's at least my understanding. And by the way, in Abrikosov, Garkov, Zelashinsky, there is another theory. In other books, there is also another theory. So I haven't seen exactly this theory and exactly this notation in some other books right now. But I also wasn't especially searching for it, just like how much experience I have, not so much to tell you where else this is written. But also it's a relatively useless question. You can just use this method and not even ask question about where this method is also written. So we have this formula for the Green's function. These are relatively famous formulas. We have also a matrix notation right now, where, yeah, basically our matrix Green's function is like 2 by 2 matrix where we have non-diagonal components are 0 and diagonal components non-zero. These are the expressions, so we will return to them later. Right now there is not much sense to think deeper about them. Yeah, but okay, also didn't give much comments, but suddenly that definition of the gap becomes a gap equation if you plug the anomalous Green's function here. Maybe it should be, yeah, that's exactly what is done here. And well, this equation looks rather complicated, but that's okay. Let's compare it to the well-known equation for the gap, like this. And now I should again complain that synchronization is broken, but it should be not very broken. Is it broken? No, no, no. Usually I don't scroll, I just open the proper page. Okay, maybe I was scrolling to the wrong side. Actually, I was creating this application not to ever get lost information, to find it very fast, but if synchronization in LaTeX file is broken, then I can't really do anything, so it's better to remember that we need 119 page. And yeah, that's already the theory that we don't really need. Okay, I will be scrolling for a long time. Okay, finally, there is the BCS. I was scrolling to different side, I guess. So before we had this equation, which is a famous gap equation. Uh, okay, I can comment many things, but let's just look at it. That's the gap equation that we had before, and right now we have this equation, which looks actually not like. Okay, I see that. Oh, I should have created chat somewhere there in some another place because it's overlays with the formulas. But okay, that's the one version of this equation. That's another version of this equation. It's very not obvious that they are the same, but there is a sum over Matsubara frequencies. So it's not also obvious that they are different, and common sense tells us that they should be the same. And then Levitov tells us, hey guys, do whatever you want, I will not tell you anything more. I just write you this formula and go on, do science as much as you can. Okay, then there is some matrix notation, which is rather specific, and it's like a similar notation but in matrix form, so it's better not to comment unless we meet these formulas. So that's the introduction to Green's functions from perspective of Levitov-Shitov, and currently I haven't thought myself enough about it to rewrite it in my words. There are a lot of comments that I can make about this theory. That is, a lot of things are not obvious, a lot of things are not explained, but you will not get a better explanation from textbooks, because that's one of the typical textbooks about condensed matter. So now there is a proposal to revise what's going on in superconductivity from the perspective of Abrikosov-Gyrkov. And like Levitov-Shitov is citing Abrikosov-Gyrkov-Zelensky book and assuring us that that's exactly the theory that is used in that book. However, right now we will see that no, it's not the case, and it's the very different theory. Before I was telling you about vortex part, by the way, that yeah, by the way, let me remind you this thing. Yeah, that there was this idea that we have some scattering because we have this interacting term of Hamiltonian, and scattering is reflected to vortex part, and that's the equation for vortex part. Then we have a series for vortex part, then we get the I don't know actually what we're getting from it. Yeah, really, I don't know. He just left and told nothing about it. So here, Abrikosov-Gyrkov write something similar. That's the vortex part. Then there is some diagram that is unfortunately missing in this note, but it's there in the original book. The problem with this theory is that really no one needs this. Everyone forget this. No one will reproduce this theory by heart. It's like old dead encyclopedia of specific methods. But you have some always statements that this is a useful theory, so I believe these statements, and that's why I also tell you this, because like a lot of people will claim that it's a useful theory. However, if you ask them again, like, can you derive something or derive exactly this, they will not derive. They will say I'm too busy, which means that they don't know how to do it. But okay, the idea here is the same, that we have some scattering, and for a different approach, we get a different vortex function, and then we transform this vortex function in a complicated way. And finally, we also, by the way, call it a Beta-Salpeter equation because of, I don't know, some another theory about coupled particles. And typically coupled particles are described by like this equation, which is here not written. This is Beta-Salpeter equation, but we call, I mean, in another place in Levitov-Shitov, it's called Beta-Salpeter equation. The idea is that we evaluate the vortex function as some either vortex function and plus some combination of it and some Green's functions. At least that's what I understand. Yeah. Then I don't know what to comment about it, because that's really exotic theory. But finally, the idea should be really the same, that we have some scattering, we have some interactions, and interactions like can give us instability. To get instability, we need the vortex part, because that's how we really what we really believe in based on Green's function formalism. And because of some mathematics, like very peculiar mathematics, we just get this equation for vortex part. And there are some constants here, like lambda is from Hamiltonian, free momentum is also because we have a lot of electrons, and some of them are in Green's functions that we plug to the Betzel-Peter equation. We get this Fermi momenta. So maybe it's not really essential how exactly this thing is derived, because it would take me, I don't know, like 3 hours to really think carefully how I can derive this equation. But somehow we can get this equation, and we also right now are interested for some reason for Q equal to 0, because maybe that's the low energy vortex part, and we just do transformations. And again, after transformations, we get like some equations in the form of a pole. Again, some transformation. Just want to find out. No, really, I don't understand what's going on here. It's just some transformations of vortex part. It's not really easy to understand, but the idea is that we just look at vortex part. Maybe I will come back to this equation. But you see, like, that's very different comparing to what we have seen from Levitov-Shitov book. Okay, maybe we will see right now how we can determine a transition temperature. Before, as a reminder, we used Matsubara's susceptibility, and there was a divergence in it. Here we have the same equation for vortex part, but for finite temperature, and we use Matsubara Green's functions, because like if we have finite temperature, we yeah, maybe I'm missing some good conclusion from this part, because it was for 0 temperature, so maybe maybe some good statement here is present, which I don't really know right now. But I'm sure that nothing goes out of this statement. Then, like if we have finite temperature, we use the same formalism, but for finite temperature, we plug Green's function at a finite temperature, and uh, mm, and I guess that the same here idea is used. We just transform a part of vortex function, and we have an equation for the full vortex function, but now for finite temperature. So maybe the previous chapter from Brikosov-Garkov was about the same thing, but for 0 temperature, and for 0 temperature maybe they claim that there is just instability, because it's always easier to write some transformations for 0 temperatures and then only to move to finite temperature. Maybe that's exactly what they were doing. But for finite temperature, the idea is the same, that we stick to vortex function, then we find the expression for it, and for the pole, yeah, for the pole, we just see for which temperature there is a divergence. Where is the temperature here? Okay, there could be also some typo here. It should be actually T here, because this equation comes from this equation. You also don't see it because there is a chat overlay. I'm sorry. Next time I will decrease the chat. So from this equation we have the transition temperature, because the philosophy is the same, that we want to to have divergence of scatterings, to have a bound state, and divergence is when denominator is 0. Okay, right now we are coming back to Levitov-Shitov, and right now actually maybe we have a really good preparation because we have seen shortly formalism of superconductivity from Levitov-Shitov, formalism of superconductivity by Abrikosov, Garkov, Zelashinsky, and we haven't seen something that we really don't need because there are a lot of things in Abrikosov, Garkov which go way beyond what we will see here, and that's Cooper instability problem from Levitov-Shitov. Of course, it's solved there, but nothing is explained there, and they really tried for some hours or days to understand how this approach is connected to, for example, this approach. It looks, of course, somehow similar, but it has many features that are not present in Abrikosov-Garkov. Okay. So, and this is the solution. So we are asked to prove that there is a Cooper instability in the BCS model at maybe zero. Oh no, maybe at finite temperature. Let's check. Yeah, it's a finite temperature thing. So they tell us that for some reason this vortex part is also factorized. I'm not sure why. I don't have some physical intuition. Why is it so? But that somehow works. And also they say that this is the ansatz for some functions of vortex function. You can ask me that there are no reasons for this to be true, and I can agree, because in book of Levitov-Shitov there is no reason to be true. For it to be true in Abrikosov-Garkov there is also no reason for it to be true. I mean, I don't see, there is some physical intuition which is not written here in both books, so I can't tell you why is it so, but what I know is that that's what they propose to get the results of this one exactly result, but from the previous approach where they use scattering, like these diagrams. Okay, like we have already seen the susceptibility approach, we have already seen the like Betz-Salpeter approach, but here it's like still Betz-Salpeter approach, but with some special ansatz which is not really explained. So we are proposed to start with Betz-Salpeter equation, then maybe write this equation for finite temperature, then plug Green's function, two Green's functions here, and get the Betz-Salpeter equation for in this form where yeah well this is the vortex part that we need. That's the vortex part if we had just one term in our diagrammatic series, and this term is from this side of Betz-Salpeter equation. We just plugged Green's functions and did some integration, which should work. Of course, it would take, I don't know, at least half an hour to understand step from here to here, but we need to believe authors of this book. And now we use the ansatz. If we use an ansatz for gamma 0, then we get this equation for gamma c. Then we use again ansatz for gamma c. Yeah, 1 second. I'll just reply on Telegram. 1 second. Okay, I'm back. So that's the equation for vortex part, and the idea is exactly the same, but now we see that the formalism is different, and like a lot of questions appear why we can like use a different formalism, but okay, we can somehow, and the idea is that again we need to find the exact expression for vortex function, and we use these ansatz again because of some really unclear reasons, but if we use this ansatz, then we have a term in front of the full vortex function, and this term can be found from the equation that we had. And again, like to get the divergence, uh, we see we're looking at poles of the vortex function, and here again, like that's the good thing that I didn't close the gap equation. It's also a very nice exercise, right? Actually, maybe I have even written this exercise in my list of exercises in these notes, to look at the gap equation and tell explicitly how this thing is connected to this thing. Because, of course, this is the same gap equation, and soon we will see that the critical temperature is the same as, okay, I'm not sure, let's see, yeah, it's a critical temperature is the same as what is obtained from this equation, but they look really different because there is v squared, and we are also given ansatz for v. Yeah, like the problem with this theory is that I haven't yet seen this theory in some other place, and it's not explained here why at all we're doing what we're doing. Because mathematically, yeah, we can just plug, but physically, we have no place where we can get this formula. Maybe we can have some intuition that V should just decay as a function of energy, and this is the decaying function. If we increase energy, then V goes to zero, if epsilon goes to infinity. But it's not obvious why we're doing exactly this substitution, but that's what we're told to do, so I can't comment more about it. Okay, then if we again use some mathematics further for this equation, we're getting the critical temperature. Because critical temperature sits here, and yeah, because exactly the pole of the vortex function is the place where we have a critical temperature. That's why everything here is about critical temperature. So it sits here, but like it's also a very nice mathematical exercise to use this equation. We have just summation, constant, and some constants like the Debye frequency is a constant, lambda is a constant, density of states on Fermi level, nu zero is a constant. Yeah, so it's a purely mathematical exercise, and right now, of course, there is no sense to comment how it is done. And actually, I would not do it immediately if you ask me, like, take this equation, give me this result. No, it's very not obvious, but straightforward from this step, we get this step. We just need to get expression of TC in these constants. Maybe there are two actually ways. This is approximation and more exact one, which gives us an exact result. And by the way, here, as far as I remember, we say that the Green's function approach for superconductivity is better than a Pareto approach. Let's try to see if no, I didn't write it here in the collection of K formulas. But as far as I understand, I heard that this is an exact expression, and this is the expression of gamma. C is the Euler's constant. That's this constant. So you maybe will not be able to derive this equation at all from this formalism. I'm not 100% sure, but I'm 80% sure because that's what I heard of. And maybe I also saw it, but I was working with these formulas like a year ago, so they're not fresh in my mind. But as far as I understand, even this one is impossible to derive using just Bogoliubov transformations. Because in general, this equation is used for gap at zero temperature. That's equation, okay, it's not written here, but should be written that this is the gap at zero temperature. And there is a relation between critical temperature and gap at zero temperature. But there is, okay, I'm not sure how we can derive this formula. Okay, I'm 80% assured that it's still impossible to derive this formula with this constant from just Bogoliubov transformations. Maybe later I will mark myself somehow, but right now that's what I think. So, okay, in scope of introduction of superconductivity, there are several approaches to Cooper instability, and maybe right now it's not really a cool topic to focus on. By the way, if you have some questions, you can write, or some comments, you can write, because I will understand how well someone understands it, if there are at least some viewers. But yeah, like Cooper instability, basically you see like that's the Cooper instability from view of Levitov-Shitov. That's what exactly we should do based on that theory. Based on another book, which was written by two German scientists, Bruce and Flashberg. It's actually not a really famous book, but it has some good explanations. Um, yeah, we have a different approach to Cooper instability, and in this approach, we are doing some transformations of a wave function, and maybe it's better not to even focus right now about this. Okay. Yeah, what to tell about it? Oh yeah, like that BCS formalism that I jumped through is well, it gives us this wave function of a Cooper pair, uh, which can be obtained by action of these operators. Yeah, maybe it's better not to speak a lot about it, because yeah, there is such a theory, but um, uh, I don't know any conclusions out of this theory, and yeah, we just deal with wave functions, so I'm not really strong about this theory. We can get the eigenvalue, maybe. Okay, let's just keep this theory. It's just anyway introductory one. That's, by the way, a typical plot of the spectrum of the particles. And that's actually a typical theory of Cooper pairs. I have this theory in another place, actually, in my note, but here it's also a typical theory that we have just a Hamiltonian, free Hamiltonian for both particles, then their potential, which is not yet written here. Um, Yeah, like you see, after learning a lot of things about Green's functions, it's not really obvious why do we need at all this theory. Yeah, there is a quantum mechanical approach. Oh, that's the interaction in Hamiltonian is just a constant in momenta space for several momenta. Um, ta-ta. And now you can also ask me why this formula is so, if we said that we work with phonons, and the typical answer is that the interaction potential is non-zero near Fermi level. That's what's written here, P0, and there is a device window. Okay, maybe it's better to stick with this explanation. Okay, the idea is that we just solve Schrodinger equation. I mean this one Schrodinger equation for with this free Hamiltonian. Dun, dun, dun. Pum, pum. Yeah, okay, I actually forgot how this works. Somehow we also get the gap. That's the main conclusion, that if we work, but gap at zero temperature, right? Because we don't have a temperature. I'm not sure how to input temperature to this formalism. It's just a Schrodinger equation for coupled wave function. It's actually a toy model, and I think useless model because I haven't seen this model ever in other places. But it's a canonical model that tells us that if we have this attraction, then if we have such wave function, we can use this ansatz for a wave function and find the coefficient and uh, um, and use this equation for coefficient to get some equation for the gap. That's how it works. And finally, we have an expression for a gap at zero temperature. And there are some comments about mathematics. Okay, let's maybe finish with the system of fundamental equations for a superconductor. And idea is that again we start with the electron phonon model. Then like we can act on psi or psi dagger if we go to Heisenberg representation. And if we act with this Hamiltonian, we just get this equation. That's how I understand it. And that's the equation which we want to solve when we introduce our Green's functions. So as usual, like we put delta at the right side, and instead of psi, we put a Green's function. And then we use perturbation theory for the interacting term, and maybe averaging. It's also really not very clear if we are allowed to average this way. I mean, of course, that's the correct formula, but it's not obvious that Wick's theorem is applicable here. I think Wick's theorem shouldn't be applicable. So easy decomposition into diagrams is not working. And then this is the place where anomalous Green's function appear, I guess so. Then there is this famous statement about approximately conservation of number of particles, n plus 2 and n. Uh, okay, I'm not really strong about these ideas here, but what I know is that that equation before, which had some averaging here, is now written in this form. where we have anomalous Green's functions. And this is the definition of anomalous Green's functions. And the same second equation can be written like this, but again, like anomalous Green's functions, and the Green's function is switched. Boom, boom. And these are these equations. Now we know that there are such Green's functions, so we have seen actually this theory from Levitov-Shitov, where we had finally similar expressions for Green's functions, and again connection of the gap with the anomalous Green's function. And then we do some transformation, and then again some transformation. Okay, I'm not really strong, I just know that here from these expressions we can get the famous gap equation, and you can see that that's approximately the same equation. We have like 2 pi to the power of 3, and also minus yeah, and I'm not sure really how to explain the minus, but I was thinking about it a year ago. So somewhere there in my head there is a knowledge about why this minus is here. I mean, here we have minus, here we have minus, here we don't have minus. Okay, let's not focus much on this. So that's how we can get this exact expression of the gap and critical temperature. And by gap we mean gap at zero temperature. That's how it works, that we act by, I mean, not act, but just, yeah, like write equation for this Hamiltonian and then use complicated ideas which I didn't explain because they're really deep about some averagings, that we can rewrite averagings in terms of anomalous Green's functions. And then together we have coupled equations of Green's function and anomalous Green's functions. And from them we derive expressions for Green's functions. Then we look at the definition of gap and see that that's exactly an expression of anomalous Green's function. And we just plug the anomalous Green's function and get the gap. That's the summary of what happened here. Also, we can write these equations for case of external field, and that's like really useful. I hope that it's really useful for equations of penetration of field to a superconductor. I think I saw uh, uh, maybe Larkin's article about penetration of high frequency magnetic field or electric field to a superconductor. So a lot of things have been discovered in this field, and I guess in this direction. What if we have a current that penetrates superconductor? And well, these equations could be used there. I didn't check right now because it's a very specific question, but okay, sounds like we now have a strong background about how this happens. And okay, there is a superconductor at finite temperature where we use the same formalism, but now we have also averagings, and we have similar equations, but now for Matsubara Green's functions as usual for finite temperatures. But also we write in the matrix form. Then we go to Fourier spaces. We get similar expressions for finite temperatures, and we plug to the same gap equation anomalous Green's functions, and we get the typical well-known gap equation for finite temperature. Yeah, I forgot to tell you that this here is an equation for zero temperature because I wasn't editing this summary of key formulas. Okay, so I think it's nice point to stop. So let's revise what we went through. I shortly discussed general introduction. I shortly discussed the basic effects of superconductor. Well, I told you as much as I know about Green's function method, Cooper instability, calculation of transition temperature based on Betzel-Peter equation, also some Hamiltonian type approach to Cooper instability, and then I finished with system of fundamental equations. And there are a lot of things actually what happens in theory of superconductivity, but it's like for a lot of many future streams if there will be a desire. So that's how superconductivity works. Maybe I can open some formulas here about it. To summarize, finally, a lot of things that I was imagining. I didn't explain actually the plots because it was meant like a more theoretical stream. And it was all only about BCS theory. I didn't tell anything about Ginsburg-Landau theory. And there are a lot of phenomena that are only driven in scope of Ginsburg-Landau theory, or at least it's nearly impossible to derive them in BCS theory. Yeah, there is this formulas for the Hamiltonian. Yeah, there is second viewer, but sorry, I will soon finish the stream because I have told already a lot of things about, for example, the Hamiltonian approach to Cooper pair instability, and also for the BCS theory that yeah we can from one side derive diagonalize BCS Hamiltonian and get the gap equation. From another side, we can use the Green's function formalism, which is not really written here. There are just Green's functions. But that's the best thing I can tell you about superconductivity because that's really a big topic. Where is it? Yeah, it has really a lot of things. Yeah, but okay, that was a nice stream. Thank you, everyone who joined. Really, everyone. I enjoyed talking with some of you and with all of you, especially with Mr. Love Peace. If I do like this, maybe now I'm switched. Yeah, now switched to another window. So thank you and bye bye. Next time I think it will be somehow better than this one. I will make not such so big chat. Also, maybe I should announce more for proper people. I mean, for interested people of this topic that we're going to discuss this topic. But in general, it was a nice time. So bye bye.